All right, we have everybody back. Hi, everybody, and welcome to this Dawn Mission Hangout. I will be producing the show today. My name is Nicole Gallucci. I'm a postdoc with CosmoQuest, and we are joined by Brittany Schmidt. Brittany Schmidt from the Dawn team, so you guys all remember her from Georgia Tech. Hello.
Hello.
And with us from the Dawn team also, Whitney Cobb. Hi, Whitney. Whitney will be taking your questions via Twitter today. And we are joined by our two guests, Kristina Larson. Hi, Kristina. And Kareem Badaruddin. Hi, Kareem. Awesome. So we are going to be talking about the Dawn testbed today, and as usual, you can leave us questions using the Q&A app if you're watching this anywhere on YouTube, on Google+, or anywhere that it's embedded. Click where it says join the conversation on your video to use the Q&A or question and question and answer app, sorry. Send us your questions, send us your comments. We will try to get to all of those in the show. If you're using the question and answer app, there's a little 9-square Rubik's Cube looking icon. You can switch between the Q&A app and the Showcase app. The Showcase app has some of the cool links that we'll be talking about during the show. So I see a couple of comments already in, and hellos. Hi, everybody. And why don't we get started with a brief overview of the Dawn mission from Brittany?
Sure. Well, thanks everyone for joining. It's a pleasure to be hanging out with you all again this afternoon. This has been a fun part of the Dawn Mission Education and Public Outreach team's work for the last couple of years. So for those who are new to the Dawn Mission, it's a really, really exciting thing to work on. So the Dawn Mission is officially the first spacecraft to go to 2 different primary objects. It's actually headed to 2 targets in the main asteroid belt. In fact, we've already visited Vesta, and you may have seen some of the really amazing high-resolution pictures that we took while we were there. Other data, including spectroscopy and gamma ray and neutron detection. So really exciting trip that we had there at Vesta. And in fact, right now, we've left Vesta, first spacecraft ever to leave one target and move on to another, and we're on our way to Ceres. So we'll arrive at Ceres early next year. I'm expecting a very different type of body when we get to Ceres. So Vesta is the largest basaltic asteroid. Basaltic means it's differentiated. It has an iron core and a silicate exterior, a lot like the Earth does. When we get to Ceres, what we're expecting is something a little bit different, with a silicate interior that probably hasn't melted yet, probably an ice layer or even an ocean on the outside with an ice shell on top, and then another layer of muddy or clay-like material up on top. That's our guess. But we're not going to figure it out until we get there. So really exciting. So we're on our way to Ceres. Really glad you could join us to talk to us about or ask questions about how it is that we plan and we get ready for these things. And so we've got some experts from JPL who are going to tell us exactly what it's like basically to play Dawn from the ground to make sure that everything works when it gets up to the spacecraft. So thanks for joining us, and I hope you have a really great time.
Kristina, do you want to get started telling us who you are and what you do at JPL?
Sure. So my name is Kristina Larson. I'm a systems engineer on Dawn, part of a team of 3 people that do systems engineering. And I started on this project as an intern, summer intern in 2008, which was shortly after Dawn launched. We actually just celebrated the 7th year launch anniversary. Last week. So yeah, I interned every summer. After that, I worked part-time throughout grad school and been working here ever since. I studied aerospace engineering at USC and did my bachelor's and my master's there in aerospace engineering. And yeah, I've been loving working on Dawn. Some of the things that I do as a systems engineer on Dawn are I build sequences to set up. It could be anything from our normal routine background sequence or special activities like testing out new heater set points or anything like that. I review sequences, I test them in the testbed, and I help keep the testbed configuration up to date with the flight configuration. So yeah, that's a couple of the things that I do.
Cool. Kareem?
Well, hi, my name is Kareem, Badaruddin.
Do you want to switch mics?
I'm going to switch mics.
Yeah.
My name is Kareem Badaruddin. I have been at JPL for 20 years. Worked on the Dawn mission, about 5 years now. And most of the work I've done at JPL is managing test beds for different missions. What I do on a daily basis on the Dawn mission is I make sure that the test bed operates properly, maintain the hardware. It's kind of takes a lot of TLC to keep this hardware operating properly. Our simulation requires a lot of looking at and maintenance. So there's a lot of work to do to keep the test bed up and operating properly.
Cool. So what is a test bed, and what's its role in spacecraft operations?
Glad you asked. We have a nice little slide that talks about what is a test bed. If you could show that while I talk to it. And I think the big thing to know is that a test bed, or rather a spacecraft, is full of computers. These computers are custom made to do a specific job. So it's not like a laptop that could be running word processing software or a browser or Google Plus or whatever you like at any given time. These computers can only do one specific thing, and even the computers that are on board Dawn, they're designed just to operate the Dawn spacecraft. And so we're interested in testing the different things that we do on the spacecraft, and it's a whole lot easier and faster and cheaper to use actual computers than to try to simulate them with software because they're so highly specialized and so complex. So we have computers just like what we have on the spacecraft here in the test bed. Now the problem with using them is that since they were designed to fly in a particular spacecraft, we have to build the test bed to simulate all of the signals and other things that the computers are expecting. Otherwise, they won't function properly. So that's kind of in a nutshell what a test bed is and how it works. Quite a lot more to it, but that's sort of the top level.
And so what's the use? How is a test bed useful to the mission? So you can't actually do work on the spacecraft itself. So what are you doing in the lab?
Can you take that?
As you know, Dawn is super far away, so we can't. Our one-way our round trip flight time right now is almost an hour. So once you send something up on the spacecraft and it starts executing, there's really no taking it back and no adjusting things on the fly. So, and we send up sequences sometimes that last a month. So you really want to make sure that everything you're sending up, there's no mistakes in your commands, that all the hardware and everything's going to react in the way that you expect. So if we send anything up to the spacecraft that's not absolutely routine, we test the test bed. And our test bed runs in real time, so we can't speed anything up, and so you really have to plan out your tests thoughtfully so that you can actually observe what you want to observe. And we look at our tests really carefully. We query all the data. We look at the event messages that get spit out, just to make sure that we're not doing anything. So this prevents us from just making mistakes on the actual spacecraft.
So you guys are 7 years down the line since launch. So I assume at the beginning of launch you don't have the entire every step planned out. What kinds of maneuvers or things have you had to do on the test bed?
Like special activities?
Mm-hmm.
Man, there's been a lot of special activities since 2007, but things like when we weren't able to use all of our reaction wheels, some of the engineers developed a special attitude control mode called hybrid mode, which uses both the hydrogen jets and 2 reaction wheels. And this was like software change.
Oh, I think we just
Intensively vetted and tested on the test bed, and along the way you try one version of the sequence and you see it saves the spacecraft, and you got to go back and tweak something in there, and by doing that they were able to come up with this new way to control the spacecraft when we're at Ceres.
very cool. So what kinds of things make up the test bed? What kind of hardware is in that?
So I think we have a nice slide that talks about the actual hardware that's in the test bed. Now, again, the spacecraft has even more hardware, more devices, more computers than what we have in this test bed. But what we have here is the central electronics unit, which is, you can think of as the pilot, basically in control of most of what's going on the attitude control, controlling when we're going to send information to Earth, that sort of thing. And there's 2 of these. They're redundant, so that if one failed, we'd have another one. Then we also have the and we call that the CEU. Then we also have the attitude control electronics, which we call the ACE. This is essentially a co-pilot. It handles a lot of lower level functions that help out the CEU to do its job. Then we have the digital control and interface unit, which we usually call the DCIU. That's basically the chauffeur. It's the driver for the ion propulsion system. So it basically puts its foot on the accelerator. We do an awful lot of thrusting on Dawn, and that's the guy who's doing it. The framing camera is essentially the photographer. Takes pictures. We have 2 framing cameras. Visible and infrared mapping spectrometer, which we often call the VIR. I call it the scientist. It's an instrument just like the framing camera in the sense that it's taking images, but I think most people can look at a photograph and know what it is, but really only scientists look at spectrographs and know what they are. So, and then the last piece of essential hardware we have here is the serial data bus. All of these computers talk to each other over the serial data bus, which we usually call the 1553. So you can think of it as sort of the moderator. So that's a summary of the hardware we have in the test bed.
And, whoops, I've lost my video. We have a couple good questions from Arvind Mohan. How much time do you guys take to test out commands and signals before you actually send it to Dawn?
Like I mentioned, if it's a routine sequence and if it uses blocks, which are kind of packaged bunches of commands, we don't have to test those because they've been so thoroughly tested, we trust them. But for any special, unique activities, we spend a lot of time testing. And it's never as simple as just getting through your test once, because on the test bed, you might have like some random error that might kill your test, and so you have to run it again. So I'd say for like a 5-hour-ish activity, it might take me a couple days of testing to really get through it.
Okay. And we also have a question from Ray. Oh, I'm going to butcher your name. Ray Boulou? I'm not even going to try. Ray, what has been the most challenging technical issue you had to overcome since Dawn has been en route, and how did you overcome it? And I assume a reboot isn't feasible.
Well, we actually do command reboots in our latest anomaly, which was our safe comm and safe mode entry on September 11th. We were hit by an energetic particle, and it hit DCIU. And this actually happened to us before Vesta, the same anomaly. And it basically turns the DCIU off, which sends us into safe comm mode. And then we had a subsequent anomaly that puts us into safe mode. And we actually commanded an OBC reset in that recovery because we wanted to restart the Attitude flight software. But that's not ideal, so we don't want to always be rebooting the spacecraft. I would say that the hybrid control was probably one of the major technical issues that we resolved by using the test bed. Yeah, that's the biggest one that comes to my mind.
Okay. Now I know we had a little mini tour of the lab planned, so do you want to show us the actual test bed that you guys have in the lab, and then we can show some of the close-up pictures afterwards? Kareem, you want to take over rolling around?
I do.
Okay. You guys won't be nearly as dizzy as when I try and move things, because they have, like, you know, a proper rolly system with their camera.
So we have 2 test beds here. You might think of it as 2 different spacecraft, if you will. So first, for any test bed, a big component is the support equipment. So this is the support equipment for one of the test beds, and this is the support equipment for the other test bed. They're pretty much the same. And now here's the actual hardware that we have in the test bed. I'm going to pick up the computer now, so it's going to bounce around a little bit. So this is one of the test beds. This is the lower fidelity test bed. And this is the other test bed. It's higher fidelity. It's got more hardware in it.
I was going to say more wires means higher fidelity, I take it.
It's more stuff.
More stuff.
So you can see the framing camera there. It's right in front of the picture. Behind the framing camera is the digital control interface unit. This is VIR, and you can see the ACEs and the CEUs back there. Again, in this test bed, as in flight, we have 2 ACEs and 2 CEUs for redundancy.
What are the ACEs?
So the ACEs are essentially, they perform some lower level functions that help us fly. So those are the ones that I referred to as the co-pilot. They do things that support the CEU, if you will.
That might be the only acronym I remember, because ACE makes me think of pilots and co-pilots. So you guys can remember that. Very cool.
So that hardware is pretty much identical, at least electronically, to what's on the spacecraft, right? So you get to test out exactly how the commands would go through those systems?
That's correct.
And we had some, let me pull these out, some close-up pictures of some of the bits. This one is the DCIU, what does that stand for again?
Digital Control Interface Unit.
Digital Control Interface Unit. So you guys took a nice picture of that.
That's the guy we called the chauffeur. He's the one who drives the ion propulsion system.
Okay. And then the framing camera as well. There's a much better shot of it here that you guys shared with us.
That's the lens cover, if you will.
Okay. Cool.
As a note, we actually have an actuating cover in the test bed that, if we wanted to, we could command it to move over.
What does that mean? That is actuating?
We have a working cover that can open and close the test bed.
Cool. All right. We actually also got a question about the framing camera. And of course, Thomas Tranakar wants to know, what are the specs of the framing camera? Do you guys have an idea of image size and resolution for that? I know that's kind of a tough one.
I don't have specific resolution numbers, but I think it's probably listed on the website if you want to look that up. Mm-hmm. If you want, you could bring up the detailed image Cornelia crater.
Sure. So, of course, those of you who might be Vesta mappers are familiar with pictures like this. Vesta Mappers is letting you help us actually map all the craters and surface features from the Vesta data sets.
Yeah, so I don't have numbers for you, but this can give you an idea of
right. So there's
yeah. So one of the things that's really interesting is that when you think about cameras, at least you think about your digital camera where you've got zoom in and zoom out. The framing camera is controlled entirely by our distance from Vesta or from Ceres. So that's one of the things that we sometimes get questions about is, why don't we have higher resolution images, or why can't you zoom into this feature? Well, it's called a fixed focal length camera. So basically, it is just taking a picture, and its resolution depends on how close we are to the target. So as we fly into Ceres, we're going to be getting better and better resolution as a function of our distance, which is why, because we're, when we're moving in fairly slowly, we get slowly and slowly better and better images. And that's why when we first start releasing images from Ceres, when we first get a chance to see that, you'll see Ceres be a little white dot for a long time. And then it'll eventually get bigger and bigger and bigger. And then we have 3 orbital phases called Survey, HAMO, which is high altitude mapping orbit, and LAMO, which is low altitude mapping orbit. And those 3 orbits have different resolutions because the camera is physically further away from the target. So that's really how we control resolution, is by distance from the target. And so those are pre-planned. All that information is on the website available as well.
Yeah, I just looked it up real quick, and at the low altitude mapping orbit, LAMO, at Vesta, we got 25 meters per pixel. We expect 62 meters per pixel at Ceres.
Cool. And since you were talking about what Ceres looks like from Dawn right now, you guys have provided me with an image of that. And look, so tiny still. There's Ceres, tiny little dot, as seen from Dawn right now. So you guys still have a little ways to go. We have a question about, in fact, the how Dawn got to where it is. Reginald Simpson asked, "Did you use the Earth as a slingshot for momentum?"
That was muted.
Yeah.
We actually used Mars. We had a Mars gravity assist in, I think, 2000. Oh yeah. But so that was what we used to slingshot our way.
Okay. And Christopher Simonson wants to know, I think this could be either personally in your own career leading up to this or overall for the mission, what kind of hardware or software experience from other spacecraft may have informed the Dawn mission in some way?
Well, Dawn was heavily influenced by Deep Space One, which used ion propulsion, and so a lot of the lessons learned from that mission got incorporated into Dawn's design. We were able to take advantage of that experience.
Deep Space One was the first major mission to use ion engines, correct?
I believe so.
That's right. So do you want to talk a little bit about what an ion engine is, Brittany?
Oh, sure. I mean, I can do a basic description.
Sure.
So, I'll give you the Mark Raymond description, which is that basically, unlike traditional engines where you thrust at given times with high amounts of energy, the ion engine for Dawn is using xenon gas, and it's basically thrusting all the time. So Mark's demonstration is always that if you set a piece of paper on your hand, that's about as much power as those ion engines have at any one time. But when you add it up over a long period of time, we end up being one of the fastest spacecraft out there. So because we've constantly got this ion engine using very low weight fuel, we can actually move the spacecraft really fast with a little bit of force all the time. And so that's kind of what makes the whole setup special.
Cool. So yeah, the ion engine is part of why you can go to one object, orbit it for a while, and then leave and go for another object. And those of you who are Trekkies may remember a original series Star Trek episode in which Spock is aghast as Spock could be, that they had come across a civilization that was using ion propulsion, which was hundreds or thousands of years beyond where they were on the Enterprise. Meanwhile, it's 2014, and we're actually cruising around the solar system with ion engines, so they are not as far-fetched as Spock would have you believe.
So Kareem, did you have any comments on hardware that you guys inherited from other test beds, or how similar ours is to, or Dawn is to other spacecrafts in that regard?
Well, the only thing I would add is that the frame of the spacecraft and the CEU and the ACE, basically the pilot and co-pilot computers, were heritage from Orbital Sciences Corporation. So they were based on Earth orbiting telecommunications satellites, I believe, that Orbital's made quite a few of. Like in the, I don't know the number, but they're not onesie twosie. There's a bunch of them, and so we took that basic satellite and slapped some ion engines on it and our instruments, and modified the pilot and co-pilot computers a little bit, but it was the essential basis for our spacecraft.
Joe Wise, who's also on the Dawn team, added in a comment that I'd like to share. One of the earlier proposals for the spacecraft was not accepted because the ion propulsion engine was considered too risky for a Discovery mission, and it was after the successful Deep Space One mission that gave the ion propulsion system some sort of heritage and helped get it approved. So you guys, yay for Deep Space One, helping you out a lot on that. There was a question, a more technical question from Josie Nemo. When you're talking about using all these computer software, what languages does Dawn use? Is there a standard, or is this something completely on its own?
I believe it's like orbital proprietary language, so it's not like Perl or C++ or something that you learn in school. But yeah, that's all I can say.
Okay. So Craig Landon asks a question that I've been thinking of as well for both of you. What path of study prepares you for test bed work? What is it? Electrical engineering, mechanical engineering, astrophysics, some combination of all of the above? Can you tell us a little bit about the path that led you here?
So what we're doing, let me back up and let me say, at least when I studied, I'm an electrical engineer, and when I studied, in different schools, I had heard from more than one professor that there were not so many ideas. There's just they just get applied in different ways. So I would say I found that to be relatively true, and so it's more like the engineering mindset than it is a particular background in electrical or mechanical. I would say that technically most of the work we do would fall under the category of aerospace engineering, but people who are trained as electrical engineers, mechanical engineers, of course aerospace engineers, computer engineers, would easily bring something to the table that the JPL would be interested in.
Kristina?
Yeah, so I studied aerospace engineering. I do different work on the test bed than Kareem does. So if you're more interested in hardware and really getting into tweaking the hardware and all that, I think that requires more of a mechanical, electrical background. But since what I do is running sequences, it's a more systems-y mindset, and so yeah, just really any sort of engineering background that's applicable to spacecraft operations, like aerospace, astro, mechanical, all those can very well for this one.
So I noticed you guys seem to be wearing lab coats, which is not something we get to do a lot in the space sciences. Can you tell us a little bit about what the lab coats are for?
High fashion, really.
Everyone will be wearing them soon. But actually, it turns out that the average person drops about 4 pounds of hair and skin off of their body over the course of a year.
I think I shed that just in hair. Yeah.
So in a clean room environment, and technically this is not a clean room. This is a test, what JPL calls a test chamber. So we don't have the higher standard that a clean room would require, where we would use a hair net and coverings over our shoes and gloves and things like that. Primarily, these coats are what's called Faraday cage. So they basically keep the electricity on our clothes inside the coat, so that as we get close to the hardware, we don't bring static electricity to the hardware. The other thing we have to do as we get close to the test bed, the actual hardware, and you might have noticed me plug in with this wrist strap. This electrically connects me to ground. So again, the electricity on my body cannot affect the test bed, because the test bed is also grounded. So it puts me at the same electrical potential as the test bed.
What would a spark or a static charge do to the hardware?
It can vary from an immediate failure, like destroying a part, to a latent failure, weakening a part. And the latent failures are the things we're most concerned with, because we might actually launch a spacecraft with a latent failure because we had not detected it. And of course, once a spacecraft is launched, it's difficult, if not impossible, to repair. So we don't want any kind of latent failure. And again, that's the hardest kind of failure to detect.
Right.
So that's why we take a lot of precautions. The other precaution we take is based on planetary protection. So we don't want to introduce stuff from Earth, viruses and things, into space. And so that's another reason for the clean room environment, limiting the number of particles from Earth that could catch a ride on board our spacecraft.
Very cool. Yeah, I was working on a ground-based telescope in South Africa, and we ran out of wrist straps, and I had to make my own out of copper tape and wire, so that we didn't damage. It wasn't in space, but it was still going to be difficult to fix, and we had 128 out there.
That's real engineering.
Yes. So we have a couple of engineers in the audience. Arvind Mohan, who we heard from earlier, is an aerospace engineer, particularly interested in how the ion engine was used to escape the gravitational field of Vesta. Does any of you have a comment on that? Brittany?
Go ahead, Kristina.
Well, I was just going to say, I mean, it was just our trajectory was just carefully planned by the navigators, and it's a slower escape maybe than with the conventional fuel engine, but we're still strong enough to get us out of Vesta's gravity.
Yeah, it's a little bit different on Dawn than it is on some other spacecraft, because we basically just kind of changed the orientation a little bit and then thrust in a slightly different direction in order to do that. And it works for us because we're going to two relatively small objects. You need a lot of force to leave an object with a bigger gravity well, for instance. But with Vesta and Ceres, even though they're huge for asteroids, right? Vesta is the size of Arizona, Ceres is the size of the state of Texas, giant asteroids, they're still relatively small gravity wells. So we can kind of turn on the engines and thrust for a long period of time. And we have a little help from hydrazine as well, so we can have a little extra impulse, and then we basically just cruise. So it's just the same way we came into Vesta, we kind of spiraled in. We also spiraled back out, basically, a long trajectory, and then we'll do the same thing at Ceres, at least to get there. So, and there's diagrams of that on the website as well.
So here's one diagram of the trajectory. So we start with launch from Earth. And then there's a spiral out. Here's the Mars. Oops. Here's the Mars gravity assist that you mentioned. Another spiral out. Arrival at Vesta. You guys spent a little over a year at Vesta before departing, and then spiraling out once more. And it looks like, is that still the target arrival date for March 2015? Or
I believe capture might be April now.
Yeah, it pushed back a month into
Okay.
April.
okay.
But just as a note, I think still by the end of February we'll have images that are at or beyond Hubble quality.
Awesome.
Sorry, can you repeat that?
By the end of February, we should have images that are at and beyond the Hubble quality images that we have now of Ceres.
So for an example of that, so we actually have a previous Hangout that's up on the Dawn EPO YouTube channel where we talked about the heritage of moving from Hubble images to Dawn images. On the left is Ceres. This is the best Hubble image that we have so far. So you're saying by the end of February, we'll be getting images at this quality or better. So even before we arrive, just like with Vesta 3 years ago when we all sat here going, oh my god, oh my god, oh my god, new pictures, you will be doing this all over again when as we approach Ceres. And
yeah, it's kind of a different thing because we do that spiral in. We call it capture. It's not an arrival in the same sense as, you know, when you have a Mars rover that launches, you've got a trajectory and you know the date you're going to land, you know the minute you're going to land.
right.
Ours is kind of, it's a little more relative. It depends on how much thrusting we get done on our way, on how much, which direction that happens to be, and whether we pause to do some other testing or something like that. So it's a little bit different than traditional spacecraft arrival, but that's why we kind of give you a window that's, you know, late March, early April time, when we're going to start having what we call a capture, and then we'll be spiraling in over a little while, and then but they mentioned that the images get better than Hubble in February, so that's a thing to start thinking about or start looking forward to. Really, you know, slowly getting better over time.
Yeah, and there is, in the Showcase app right now, if you guys are using the Q&A app, you could switch over to the Showcase app as well. We've got a couple links that it's cycling through. One is the Dawn blog, and another one is actually the picture showing the live location of Dawn in the solar system, as well as what Ceres looks like from Dawn as well. So you can check that every day if you want and kind of follow along. So Jose Ramirez Garcia asks, how long does it take to develop a mission like this? It usually takes a lot of time, but he's curious more about how this mission was developed before launch and maybe how it has continued to develop since launch.
Well, this mission was proposed actually several times and in different ways before this one was even selected. So we were selected in, is it 2001, I believe? Was when
Look back behind the
we actually got selected. But so the proposal process is kind of where the scientists and the engineers come together, and you work on the concept for the design of the mission. You think, all right, if we're going to go, I really want to know this science. What do we need to do that? And so that's where you plan the mission itself. So you pick out the instruments, you pick out the people that you know work on those instruments really well, and then have engineering teams that are really great at building those types of instruments. And then you partner with a spacecraft company. In this case, we're using Orbital. So we mentioned, Kareem mentioned the heritage from some of Orbital's other spacecraft. So I think this is Orbital's first major planetary mission, building a spacecraft. So that was pretty exciting. So Chris Russell is the PI, basically gathered a group of scientists and engineers, including Jet Propulsion Lab and Orbital Sciences, who helped build the spacecraft, and then got these ideas together. They proposed it a couple of times. Dawn's what's called a Discovery class mission, which means it's the smallest class of interplanetary spacecraft that are considered like a major mission for NASA. So it's a big hurdle to get through, actually. And so once it's selected, then from 2001 till launch in 2007, it's science planning and engineering planning. That's when you actually build the spacecraft. That's when you actually build the instruments. And then once launch takes over, then it's people like Kareem and Kristina who are doing test beds, trying to make sure everything works, doing checkouts for the instruments, doing all that stuff. So they can probably tell you more from launch. So from the scientific perspective, we kind of say we want these images, we want them to be taken right about now, we'd like this kind of thing to come back from it. So we think about it that way, and then we pass it over to the engineering team, and they're the ones that do the implementation. So they can speak more about that.
Sure. Well, I joined the mission kind of just after all the initial checkout activities, but I know that right after they launched, there were a lot of activities they had to go through, just
Hang on, we're losing your.
You're up.
Yeah, do you want to scoot on over and try the other computer?
Is the mic not working?
Okay, try again.
Can you hear me?
Yes, try again.
Okay. Okay. So I was just talking about the initial checkout activities that happened after the launch. You have to check out all your hardware, all your redundant hardware, and make sure that everything is functioning properly. So there's probably a month or two of activities that you end up doing after you launch. And even after all that was done, in the years that it took to get to Vesta, there was a lot of work that had to be done just to be ready for Vesta that hadn't been finished before launch. Just developing different processes on ground, sequencing, figuring out how we were going to do sequences when we got there, and all of these strategies. So yeah, there was still a lot of preparations that had to be done.
We have a question. I think this came from Twitter, from Yak Dreams. I hear the test bed is pretty chilly. Why is that?
I'll take those.
Okay.
This is darn delay on my button.
There you go.
All right. So the flight hardware is designed for a very it's designed to be very robust. The space environment is very harsh, very cold, maybe very low pressure, like a vacuum, and so we use electronics that are very robust and can handle a lot of different temperature extremes, pressure extremes, all of that kind of stuff. Now, I mentioned that in order to use this flight hardware, we have to build support equipment that simulate the space environment and that simulate the other systems on board the spacecraft that we don't have hardware for. Now, of course, it's much cheaper to use less robust equipment, but the trade-off is that this equipment is less robust. So one of the things that means is it likes to stay cool. It operates much better when it's cool. So we have to keep the test bed cool to protect the hardware, the support equipment hardware primarily. It ends up being a difficult environment to work in because now it's cold for people. But in some respects, we're putting the hardware ahead of ourselves.
That is something you have to do sometimes.
Absolutely.
I understand that one.
But we get paid more than the hardware. So.
Sizzlebread23 asks about testing. How often do unexpected events come out of testing for you that require some new understanding or new planning? Or do things pretty much run as you expect them?
I would say probably almost half the time we get surprised by things that we see, and that's why we keep testing things in here. It's just such a complex system, the spacecraft, and yeah, quite often we'll have to really dig into our tests and see why certain things happen.
Okay.
Yeah, I'll add to that you know, one of JPL's beliefs is that testing improves reliability. Mm-hmm. I mean, we had the question earlier, you know, what do we get out of the test bed, and how the test bed was designed. I mean, originally when we started looking at how we're going to run this mission, we had some ideas that, oh, the test bed will probably come in handy, but it's really difficult to say. We were planning, you know, 4 years before the fact to use the test bed to test this particular sequence or this particular activity. It's more like, think of the test bed as a tool, and people like Kristina and myself as tool users. And by having a tool and people like us available, the project has some creativity and some options at its disposal to solve problems, to anticipate problems, to discover problems, and to make the mission more reliable.
Ray asks, I assume that consumables on the spacecraft are power and fuel. Are there any others? How much wiggle room do you have in terms of consumables on a long mission?
There are a lot of things that we track as consumables. Things that you might not think of, like cycles on certain heaters. There's things like how many times you can start up the reaction control system thrusters cold. That's a consumable. There's a bunch of things that we track. And so we're doing really well with all of our consumables. We're well within range, but on a long mission, we launched 2007. We're going out through 2015 to 2016. You really have to plan carefully and keep track of all those consumables because it could be really easy to run up against your hard limits.
Okay. And Josie Nemo asks, when there are late failures, what kind of workarounds or fixes do you have to make?
Well, when we send up something that doesn't act like how we expected, and if something bad happens on the spacecraft, we go through, since it's in the safe mode, which usually the real bad things do, we go through a safe mode recovery, and it's a many-step process. Depends what kind of safe mode you entered into. You had an OBC reset, a side swap, and the whole process of recovery, we test step by step in the test bed as we go along. So we'll be recovering for several days, and before we send any of those files, no matter what it does, we send it in the test bed, and we insert the fault that happened so that the test bed is in the same configuration that the flight system is in, and be sure that everything that we're sending to recover is not going to hurt us further.
So when you hear that there's an issue with the spacecraft and engineers are working on it, it means you're probably running through tests and simulations in-house in your test bed.
We have something called the initialization script, which we call the init script, and basically it's a script you run every time you start a test, and it sets your test to start at a certain date, and based on the date you choose, it configures the spacecraft accordingly. So for example, if you're trying to test a sequence of Ceres, the test bed knows that since it's in a certain Ceres time frame, it's going to set up this thruster and make the data sets this big and set up everything for you.
Okay. I'd like to hear from each of you, Kristina and Kareem, if you have a particular experience that you had with the test bed that was surprising or something that stood out over the lifetime of the mission so far.
We had a problem where the primary kind of the big ass simulation was crashing regularly, and what that basically meant is someone was running a test and then the test just failed. The simulation just crashed. Spent a lot of time looking into it, trying to figure out what it was. And as we've mentioned a couple of times, a lot of the software we use is proprietary to Orbital, which basically means for us it's a black box. We can't open the hood. We can't get inside of it. We don't know how it works, and we can't tweak it and change it. So we're just changing the things we can and working with the things we can't change. And we went through a period of about a year with these frequent crashes that made it difficult to test and get things done. and made a lot of people annoyed and upset and frustrated. And finally, we got past that, and we started doing some regular maintenance, some things that we weren't doing before. And honestly, I cannot tell you what exactly the problem was and why we don't have it as frequently anymore. But it's just part and parcel of working with complicated systems like this.
You sacrificed the right animal to the right computer deity at some point, and it worked. Yeah.
Knock on wood.
Sometimes it feels like that. Yeah.
I guess for me, the memories that stick out being in the test bed are those weekends when you're running a multi-day test and you see it crashed and you do not want to lose your weekend that time to test, and so just coming in at odd hours and in this empty building, just kind of babysitting your test and crossing your fingers. Those days stick out.
Yeah. Oh wow. Brittany, we're getting a couple questions about the data once it gets back to Earth. Thomas T is asking, how long does it take to process and understand the science data? And Josie Nemo is asking whether we'll ever see a Google Maps version of Vesta.
Well, that's up to Google. The data certainly exists. In fact, especially for a small body, the Vesta's got quite a lot of data for it. So global coverage and just an incredible shape model. So to answer that question, it depends on what you mean by processed. So when they first come down, they're in a raw data format, and then we kind of convert it over to something we can use with our eyes. So that's the first level, right? That's level 0 processing. That's just getting it into a format that you can use. And so at some level, you can do work on that, but for some of the things that we do, like trying to figure out, even is that a crater or is that a hill? You need to know sun direction. You need to know the surface albedo. So we do another level of correction that corrects for properties of the camera or properties of the spectrometer, and then some just basic corrections, and those are called level ones. And then there's level 1A and 1B, and then there's level 2, and then much further on there's other processing. And then in addition to that, so when we release the data, it's usable by everyone. All of this data gets released publicly. So all of that's out there. All of the Vesta data is in what's called the PDS, which is the Planetary Data System, and that has all of the specs on how those individual images have been processed, or how those spectrums have been processed, or how the gamma ray and neutron, the grand data, how that's been processed. So it really depends on what you're looking for. So one of the things that we do is that you use those individual images, and then you can construct a shape model. So that's using many images and the pointing stability of the spacecraft, or the pointing direction of the spacecraft in its position, to be able to reconstruct what the shape is. So there's all levels of that. So it takes everything from a day to get something you can read, but probably has some photometry errors, or has read errors or something like that in it, and then that gets corrected. And so that first process is pretty quick, but the level 1s take a little more time. And then the 1As and the 1Bs, the types of things that get released, those take a long time. So one of the things that happens is we have some of those data, and those are the ones that we've released, like Image of the Day, and we'll be doing that again. We release those images, and those are images that are in a format that people can see and kind of check out. But the real science-usable images, takes us about 6 months to get those done. It's not that we're processing any individual image for 6 months. It's that whole process of looking at all of the images, making sure they're all okay, getting everything done on them, plus doing the rest of your job, takes a while, and getting it to a point where you can actually get it checked out and get it through a review process. So before those are publicly released in terms of the large, huge data set, in a way that they can be used by scientists, right? Not just the little JPEGs that we can send out, which we can send out pretty rapidly. The rest of that data really takes a while, because it has to go through a whole review process to make sure that the data is not only accessible, but has all of the information that a scientist or an interested member of the public would need in order to process that correctly. So an example would be, there's been some images floating around where people quote-unquote zoom in to see things on Vesta. The problem with that is that, as I mentioned, the resolution stays the same. So you can spread it out and you can dig into it as much as you think you're doing on a computer, but there's no more information than there was when you were looking at it in a full frame. And so in order to get all of the information, like pixel to pixel brightness variations, all of that we use to do the real science on the mission, that takes a little time to make sure that we've got all of it processed correctly. So it's anything from a few days to a few months to get those into shape to be digested.
Very cool. And Josie also wanted to point out appreciation for the 3D model of Vesta. So if you have access to a 3D printer, I know you guys have it up on the Dawn website. And also, if you search for Vesta on Thingiverse, you can get a free model, 3D model of Vesta. You can print your own Vesta. One of these days, I'll figure out how to print it without so much supporting material and actually have a sphere. That's my goal. So we've gotten a lot of great questions. I wanted to thank you all for coming to the Hangout. Thank you all for watching. Thank especially Kristina and Kareem for coming to be our special guests. We have a survey up. Actually, Whitney, maybe you do you have some more details on the survey while I pull up the image? It's somewhere.
I do, while she's pulling up the image. So, for us, it's enormously helpful to get your feedback on what you enjoyed about this Hangout, what was useful to you, what you learned, and also what other kinds of things you'd like to see on Hangouts. Your ideas and your interests really are important to us. So if you go onto the Dawn website, our very first slider has the image of this Hangout, and you click on that image, and that takes you to our page where we were highlighting the testbed Hangout, and you'll see a nice big fat cute button there that says, please take this survey. So if you click on that, that'll take you to a very brief, it's really a 5 or 6 questions, 5 minutes, no more than that, where you can give us a little bit of feedback and let us know about what's working and how we can improve. And additionally, in appreciation, we have a beautiful Vesta calendar that we developed. It's got images, gorgeous images from all of our different instruments on it. And we will send you an email, and if you would like a copy of that, we are thrilled to send that your way in appreciation for taking our survey.
And that link is also in the showcase right now, so it's been scrolling through along with the Dawn blog and the Where is Dawn Now in the solar system, so you can check out all of those websites. Yeah, I wanted to thank everybody again. Do you guys, Kristina or Kareem, have any last words about the Dawn mission? Maybe something you're looking forward to when it gets to Ceres?
I'm just so excited to see those first really detailed images. I remember how exciting it was with Vesta.
Yeah.
I was just in awe. Made it my background on my phone immediately and just so excited, had to show everybody. So I'm really excited.
Excellent.
And just as a reminder, we have open house at JPL this upcoming weekend.
This weekend?
This week, the 11th and the 12th.
Very cool. So if you are near JPL, totally take advantage of that, and I'm jealous of you if you are near JPL and can take advantage of that. So go for the open house this weekend. Kareem?
Yeah, I'll just say I'm very proud and pleased to be on the Dawn team, because it really is a team. It's fun to come to work. There's a lot of everybody on the team pulls his weight, and we get along very well, and it's a great project to work on.
That's awesome. That's so good to hear. Awesome. Well, thank you again for coming and sharing what you do and sharing your lab and sharing the test bed with us. And hopefully we'll be seeing you all again soon. So thank you for coming to this special edition Dawn Hangout on the test bed. Thanks, everybody. Bye.